Uh, Everything's good? You can hear me well?
Yeah.
Awesome. Okay. Hi, everyone. My name is Danica Duval, and I'm part of the engineering team here in the Wishart Lab. I started working here this January, and I'm wrapping up my co-op work term in the next couple of days. And today I'm going to talk about some of my work that I've done here for the sheep pregnancy project, so the PLS project. Sorry. Okay, sorry, there was a delay. So I'm just gonna talk about a bit where I'm from and give a brief introduction to the PLS project, explain some of my objectives for my work here for this project and some of the results that I got. And I'll explain some of the lessons that I've learned because I've learned so much here in these past 4 months. So I'm from Alberta. I was born here in a small village called Jean Côté. And then when I was about 2, we moved to Nova Scotia in Dartmouth, which is where I completed all of my elementary school. And then we moved back to Edmonton, and I've been living here ever since. I'm in my 3rd year in the mechanical and biomedical engineering program here at the U of A. And it's a great experience and a great learning experience for me. A fun fact about me is that my first language is French. My dad was born here and spoke French his whole life, and my mom is from Quebec. So I don't know if you'd be able to tell my accent, but yeah, my first language is French. So today I'm going to talk about the pregnancy detection project for sheeps. And typically, or currently I should say, the method to detect pregnancy is through ultrasound. And the technology behind ultrasound is actually quite interested me. So I thought I would bring it up here just to explain the very basics of how an ultrasound works. So an ultrasound is basically using high frequency sound waves, which are in the megahertz, much higher than what the adult human can hear at a maximum. And it uses those sound waves to convert eventually this energy into an image. And how it works, well, the ultrasound, like computer, sends an electric current to the ultrasound probe or the transducer. And in the transducer, there are piezoelectric crystals which are able to take this electrical energy and convert it into mechanical vibrations. And these vibrations form those high frequency sound waves, and the sound waves will travel through a medium, which in our case would be an organism. So when those sound waves hit a boundary or a change of medium, so going from tissue to fluid, then those sound waves will either send back an echo to the transducer, or the sound wave will keep going through the organism. And when those echo come back to the transducer, what is really cool about those piezoelectric crystals is that they'll convert back this echo from a mechanical vibration to another electric current, which is sent back to the computer. So I thought it was really cool that those crystals could convert energy in both directions. But how do we get the image? Well, based on the total time it took from the sound wave to leave the transducer and the echo to come back, and based on the speed of sound in the tissues, well, the computer can calculate the distance that the sound wave traveled essentially from the transducer to the boundary. And then with this distance, they can generate some 2D images. And of course, there's 3D ultrasounds that can be taken, not just 2D, and there's even 4D where you can also get movement. And yeah, it's really fascinating. I actually never dug too deep into the ultrasound, but I thought it was really cool. And of course, with as of with any kind of technology, there's been evolution throughout the years. So now we can even get ultrasounds done through our phones, which is really cool. Ultrasounds for human pregnancy started back in the 1950s by Dr. Ian Donald from Scotland, who was an obstetrician and a professor, and along with his colleague Tom Brown, who was an engineer, they were able to develop the first prototypes used for ultrasound technology for human pregnancy. And the technology was based on the techniques they were using for ultrasounds, but to detect imperfections in ships, which I thought was interesting. So that was in the 1950s, and then about a decade after, ultrasound was used for sheep pregnancy. Some papers were starting to come out as early as the 1966. Here are some pictures of ultrasounds from the 1969. And what I've read through my research is that in veterinary medicine, sheep pregnancy was the first, I guess, method of diagnosis they used ultrasound for, which I thought was very interesting. And the reason why that was the case, or that I suspect, is that sheep pregnancy is actually very important in the sheep industry for producers. And the reason for that is that depending on an ewes or female sheep's condition, if she's not pregnant, she's pregnant with 1 lamb, 2 or 3, the food distribution will change, and as well as the quality. And therefore, if the producers are able to know if their sheep, what are the condition of their ewes, then they can redistribute their ratios their rations of food and be more cost effective. And they can also, they're also able to, sorry, I lost my train of thought. It's okay. They can also monitor how the sheep's, if they're doing okay, if there's any issues in the, during their pregnancy, and they can detect that earlier with an ultrasound. And also they can decide whether, if they know what the ewe's condition is, they can also decide which ewes need to be rebred or culled. So therefore they can increase their flock size rate faster and get more profit in that sense. But there's a lot of disadvantages to know if your sheep is pregnant or not currently, because the only method is ultrasounds. So if you want to do, if a farmer, let's say, wants to know if their sheep is pregnant or not, they either need to buy the equipment or hire a vet. And if they buy the equipment, then they could always get training to do the ultrasound, but that's not possible specifically in Alberta, because ultrasounds must be performed by a vet anyways. And it can be also very difficult to learn for farmers, and so it can take time delays in their production, which is inconvenient. If they were to hire a vet, which is the case, well, it's especially expensive for businesses that have smaller size of flocks and that are far away from, I guess, the populated areas. And also, there's not a lot of vets that are specialized in sheep pregnancy detection, and they're more commonly specialized in cattle and horse pregnancy. So there's a lot of disadvantages. So if there was a way we could create a portable device that could be that could detect sheep pregnancy and also know or tell the farmer if they have the sheep is pregnant with a single or twins or triplets, then there would be no vet requirements anymore, and the producers could get quicker answers to therefore increase their overall revenue. So creating this portable device is currently what we're working on. So previously, some biomarkers have been discovered to detect if a sheep is pregnant or not, or how many lambs they carry. And then with colorimetric assays, we can do the reactions with the metabolites and therefore associate an absorbance reading or a color number with a metabolite concentration. And we can, of course, implement this in a device. And the device part is mostly what I was working on. But my work actually starts from whole blood and ends at the deproteinized clear serum that is then given usually to the chemistry team for them to do their assay reactions. So normally in the lab, how you collect the clear deproteinized serum is that you start with whole blood and you use a centrifuge to spin the blood and to separate the red blood cells from the serum. And then you take a certain amount of this serum and make it react with a specialized polymer. And to fully incorporate the polymer well in the serum, you use a vortex mixer. And it's important to add this specialized polymer because it'll remove some of the proteins that are inhibiting in the colorimetric assay reactions. So that's why I'm using the term deproteinized serum. And then finally, to separate the polymer from the serum, we use a syringe filter. So my job was to remove the need of expensive laboratory equipment, such as the centrifuge and the vortex, and to remove the need of handheld manipulation or specialized training. For the farmers eventually to have a handheld device so that they can just press a button or so, and everything is done for them. So first I'll talk about the methods we tried to separate the red blood cells from the serum for the blood separation procedure. So the first method we tried was using filters. So we started with the blood clot, and then we had two filtration options. So the first one was vacuum filtration, which is creating a pressure differential with a vacuum line to increase to shorten the time it takes for serum to get collected and to efficiently separate the blood clot. Or we also use syringe filtration, so using the pressure from a syringe plunger to forcefully allow the serum to go through the filter. But we had some issues with those samples. So some red blood cells leaked through, or the serum had this red color, which is very different from normal because usually serum is a yellow color. But this red color is due to the red blood cells, which rupture due to the excess shear stress they're subject to in the filter paper, or due to the excess pressure that is applied to them. And when the cells rupture, when the red blood cells rupture, we call that hemolysis. So the samples were then hemolyzed, which was not great. But however, when we took those samples under the regular deproteinization method, the samples, the deproteinized serum still turned out a clear color, which is what we normally see. So we wondered if notably having hemolysis or red blood cells in a sample during deproteinization affected the metabolite concentrations in an unwanted manner. So how we tested that is that we took a serum sample from each step of our whole blood separation procedure. And we also included a sample with hemolyzed serum with or without red blood cells. And then we took all of these samples and undertook them under regular deproteinization methods and did the colorimetric reactions with all 5 metabolites we're working with. So if the absorbance readings were consistent or of approximately the same values throughout all of the samples, then it meant that none of the steps of our blood separation procedure affected the metabolite concentrations in an unwanted way. So we had pretty promising results, except we're suspecting that there was an issue with the spiking that was done to the serum to increase the metabolite concentrations, as can be seen with creatinine, and with L-carnitine. It might also be an issue with the rapid clotting system that we have in our procedure. But it might also be due to spike serum, where we tried using NMR to confirm if that was the case, but nevertheless, the results were pretty promising, and especially for the hemolyzed serum sample with no red blood cells. So since that was the most promising, then we kept going with the syringe filtration method. So now I'll talk about how we replace the vortex as for deprotonization. So the goal was to create nice and strong mixing without the strong vortex that the equipment provides. So we tried magnetic stirring. We also tried to increase the surface area between the serum and the specialized polymer with coatings. And we also tried pipette mixing with an automated version of pipette mixing. But the best method we had was using a turbulent flow from a syringe, and therefore using the plunger for some cycles created a smooth and homogeneous solution of the polymer and the serum. So therefore we tested with the L-carnitine assay if the turbulent flow from a syringe is as efficient as the vortex. So we kept the same deprotonization protocol and the colorimetric assay reaction, but the only thing we changed was the mixing method. So the vortex or the syringe. And as the absorbance readings were of the same values, then we concluded that using the syringe was satisfactory to replace the vortex. So we noticed a similar trend in both our blood separation and deprotonization procedure, and that we're using syringes. So therefore, we thought of developing a complex of tubing and syringes that will be able to separate the red blood cells from the serum and to deprotonize as well. And since we're using syringes, it would be a disposable part of the device. So right now, we first started with 5 steps to the device, but it would not be 5 steps. The device would eventually be one piece of equipment that would do everything. But we started slowly, and we were able to test those steps in the field test. So we drove over to Olds College, where the sheep reside. And then we were able to test our blood separation and deprotonization procedures right beside the sheep. So we had very promising results, except as can be seen here, there's still some hemolysis tinting to the serum, but this can be fixed with a more uniform and consistent mixing of the syringes when they're pumping to generate the turbulent flow. And that can be fixed with automation, which is what I've been working on since then. We will use stepper motors, which will replace essentially the hand manipulation required to move the plungers. And then we can attach the plungers to the rack, and therefore the rack will be guided by the gear, and then we'll have automated syringes. And of course, automated syringes could be useful in other projects as well. And right now we do have a blood separation procedure, but still there are some issues with hemolysis. So we're trying on the side and to find a method to passively separate the red blood cells from the serum without the need of this excess pressure that breaks the red blood cells. So we're trying some specialized polymers to help to separate serum from the red blood cells, and we're doing this in the lab currently. And of course, if we can do this with the sheeps, well, the device could be useful for other animals and species as well. I've learned a lot throughout my 4 months here, but most importantly, I learned how communication is crucial between supervisors and coworkers during meetings or on a daily basis. And I also learned how important it is to plan all the aspects of your experiments, because there is always surprises in research. I would like to thank Dr. Wishart for all of your advice and knowledge that you've passed on. and Dr. McKay for directly supervising me throughout my work term here on a daily basis. And everyone in the Wishart lab that helped me, thank you so much. Everyone was very pleasant to work with. It was a great environment and to work in, and there's a lot of knowledge I could learn from each and everyone that I met in the Wishart lab. So thank you so much, everybody. That's all I have for today.